This demo is going to show you how to use Microsoft Excel's regression capability. So we have a data set here that's a different data set from the one we worked with earlier. I chose this particular one because it's got some interesting things going on. This is the house prices in a zip code that is located near the waterfront. So there are lots of different variables in addition to the size of the house and the size of the lot that are going to play into the price of the house. In fact, the size of the house is not even the most important variable. And so we're going to have to use multiple regression. In other words, a regression model with more than one input variable to predict the price of the house. And I'm going to show you how that works. We'll start out doing a single variable regression. Let's suppose that you have a lot of subject matter expertise, you're a realtor, and you understand that in this zip code, the most important thing about the price of the house is the niceness of the location, the proximity to amenities, scenic view, located in a secluded area. Those are the kinds of houses that are most highly valued. So rather than starting out predicting the price of the house using square foot, I would first probably do the correlation matrix, which you already know how to do. And what I would expect to see is a very high correlation between this variable here called grade. Grade describes the quality of the location of the house. And I have these, rather than do a correlation matrix to illustrate that, I've just sorted the houses where the lowest price houses are at the top. And if we scroll down to the bottom, we see the most expensive houses. And what I want you to see is that the least expensive houses have grade values ranging in the range of 4, 5, 6, or 7 in that area. And this is on a scale from 1 to 10. So this entire zip code is a pretty nice area. Now, if I go all the way down to the bottom where the most expensive houses are located, I see grades ranging up in the 7, 8, 9, 10 level. So if I were to do a correlation matrix, it turns out the correlation between this variable called grade and the price of the house would have been the largest one. You'll have to take my word for that. And we also find that it's in the range of 0.65 or somewhere in there. We'll find out when we do our regression model. So now let's start doing our regression model. So the first thing I want to do is to go to the Data tab, and that gets me to the tab where the statistical routines are located. And I want to go over to the analysis portion of the toolbar here and click Data Analysis. And on Data Analysis, I want to pick Regression, which is right there, and open that up. So now I need to specify for my regression model that I'm going to build what the Y value is going to be. In other words, what is it I am going to try to predict? And that's going to be the price of the house. So I'm going to put in this cell, input Y range, the range or the column that contains the price of the house. So I have that, and you notice I also included the header at the top of the page as the input, because when I get my regression model, I want to know what each of these variables mean. Now, I want to input an X range, and the X I'm going to use is this variable called grade, which tells me the quality of the location and the lot that I have. And then the regression page or box asked me for some other inputs. One is, did I use labels or not? Yes, I did. That means that the first row is a header that does not contain numeric information. The next little box over here says the constant is 0. That would say leave the intercept off of the prediction formula. In other words, just let the price of the house be a multiple of the grade, and that's certainly not what we want to do. We want to start with some base price and then adjust up or down from there based on the grade. The next thing says, do I want a confidence level? Well, we could, that rather than just giving you the estimates of the parameters, it says we're 95% sure they lie between here and here. But that's a little bit of a distraction right now. So we're going to leave that out. And then down here it says for output options, you could either put it on this same page and you would have to specify a range of cells where you want the output to go, or you could put it in a new worksheet, and that's what we're going to do. We'll just leave that as. Or we could actually start a new workbook, a new Excel spreadsheet to put that information in. If you're generating a big report, you could do different regressions and put them all in a separate spreadsheet. And then down at the bottom it talks about residuals. Remember, residuals are just the errors. For each house there's an actual value, and then our regression formula is going to give us a predicted value, and the residual is the actual minus the predicted. So I want the residuals, I want to compute those for each house. In other words, how badly did we miss it for this house? It's okay, I'd like to do a plot of those residuals. In other words, as a function of the input variable, tell what the residual was for that particular house. And then we can standardize those residuals. In other words, there will be something called a standard error, which is the standard deviation of the residuals. So we can divide each of the residuals by that number, and we get numbers that range pretty much between plus or minus 3. And if a house has a residual, let's say, of 3 or even bigger than 3, that tells you it's kind of an outlier, and we might want to go back and look as to why that's the case. And then the line fit plot is something we certainly want. It will show the input variable, and then it will plot the price, predicted price, as well as the actual price as a function of that input variable. So we're ready to do our regression now. Another option is normal probability plots. We don't want to do that right now. That's another distraction that we won't be talking about at this time. So let's go ahead and do our regression. And so now we have some very useful pieces of information. One is, here's the line fit plot, and we could pretty this plot up some if we wanted to by changing the ranges of the axis and so forth. But what I see there is this is the prediction line in the middle, and then around that you have the actual distribution of the houses for grade 4, 5, 6, 7, 8, and so forth. And what we notice is there's a couple of outliers there, and we suspect we know what those outliers might be. In fact, there's several that are up there on the high side. And my guess is, as a very knowledgeable realtor in the Seattle area, that those are the houses that are located on the waterfront. But we'll go back and check that later. And here is the plot of the residuals. And again, you see that there's some fairly large residuals in each category. So you can think of each of these sets of numbers as like a histogram for each of the different grades. For example, if I take all of the houses that graded out at, let's say 9, and look at that, that's sort of like a histogram of the prices of those houses. So now let's look at our regression information. And this is a very interesting number here to look at. The adjusted R-squared says this one single variable explains about 44% of the variance in housing prices in this particular zip code. And you say, well, you haven't even explained half of it. But you got to think, this is only one variable out of about a dozen or 15 different variables that are there. So that's not all that bad that we can explain almost half of the variance using only a single variable. And then the other information that we're interested in are these two numbers right here. Those numbers, I'm going to reformat those because those are dollars and it makes it a little bit easier to understand. Those numbers are the intercept and the slope. And it says if I want to predict the price of a house and I know the grade of the location or the grade of the lot or whatever grade is associated with, if I want to make that prediction, I start with a base of minus $343,000, which doesn't really mean much. That is not a particularly interesting number, except for the fact that it's what we use to do the forecast. It certainly says if I were to plug a 0 in for grade, I'd get a funny looking result, but we're not worried about that because none of our data contained a grade of 0. But this number here is interesting. That is the slope. And it says for every unit of increase in the grade, the value of the house or the price of the house goes up by about $115,000. So that's something that's very interesting. So this is what we call our single regression model. And for each particular observation down here at the bottom, we say this is what the price on that first house was predicted to be. Remember, that was a house, I think that first one was only worth about $160,000, and it predicted it to be way too large. So we're going to fix that by putting some more information into our prediction formula. And we look at the residual, and it says the actual price of the house was only about $160,000. So if we take the difference between the actual and the predicted, it's about minus $183,000 or something like that. And if we divide that by the standard error, that's about minus 1.22. Basically says it way over predicted that house. And if you look down through there, all of those houses on the low end got over predicted. So we got some more work to do. One other number that tells us we have some more work to do is the standard error. The standard error says the difference between the actual and the predicted should lie between plus or minus 3 of these, and that's a pretty big number, $150,000. So what we want to pay particular attention to is the R-squared, the adjusted R-squared would be a better thing to use. They're both about the same, but the adjusted R-squared is the one we want to use. The coefficients, which give us our prediction formula. And we want to remember this particular number right there, that it is telling us how much variance we've explained, because we're going to go back and do another iteration on this regression. So we go back to our data, and again, remember I'm an expert on real estate, and let's say I actually examined those houses where the errors were the largest. You remember we saw some on the plots that were way off on the high side. The actual price of the house was a lot larger than what the model predicted. And I went and looked at those houses. In other words, I found them on the spreadsheet, and it turned out those houses were houses that were located on the water. So now I want to do a regression, and I want to include another variable, and that variable is called Waterfront. Now, you notice Waterfront has only got two values. It's either 0 or 1. That's what we call a categorical value. In other words, a house can't be half on the waterfront and half off the waterfront. So the categorical variable is like a yes, no, yes, it's on the waterfront, or no, it's not. And you notice most of the houses aren't on the waterfront, but we want to find out how much difference it makes when a house is on the waterfront. So an idiosyncrasy of Excel's regression model is it requires, when you do the input variables, that all of the input variables or all the prediction variables are side by side in their columns. So what I'm going to have to do is make another column over here that has grade in it, and then right beside it put one that has waterfront in it. And I'm going to copy those variables all the way down to the bottom. And so now I'm ready to do my second regression model, and this one is going to have two variables in it. So again, I'm going to go to Data. I'm going to go to Data Analysis. I'm going to select Regression. And everything is going to be the same as what I did before in terms of what outputs I want, what the variable being predicted in. The only thing that's going to change is the input variable. Before it was in column J, I guess, and now it's going to be over here in columns Q and R. So I'll just copy that, and I'm ready to do my second regression. And we won't spend quite as much time studying this model, but we're going to look at, again, that adjusted R squared. And look, before it was what, 44 or something like that. Now we're explaining 58% of the variance, and that's good. The standard error has shrunk some. We're still have a standard error of 129,000, which is fairly large, and we'd like to get it better than that. And now we can look down here at our prediction formula, and it's changed some. For example, I believe the coefficient, let's change these to dollars so we can make some sense of them. The coefficients have changed some because before grade probably was acting a little bit as a surrogate for waterfront. It was trying to help out there a little bit. So it's got a little bit smaller coefficient, I believe, than what we had before. Let's take a quick peek. Actually, it was 114 before, and now it's 122. So actually, it has gone up a little bit. The intercept has changed, and again, it's not telling us anything in a practical sense, but it says now for each unit of increase in the grade of the lot or the grade of the location, you need to add 122,000, or actually almost 123,000 to the base. And if a lot is on the waterfront, if there's a 1 in that row or column, you add $192,000. So if somebody were to ask you right now, how much extra is it worth to have a house that's located on the water? Your answer would be, well, my best guess is about $191,000 or 191.5 or $191,506. So we still have a model that's got a fairly large standard error and doesn't explain as much of the variation or the variance in home prices as we would like. So the next thing that we might be interested in would be to say, what else is another useful piece of information that we might want to look at? Well, I don't know, but again, let's pretend that I do. And let's say, well, in this area, you know, when people buy in this area, you notice the age on these houses, they're 100 years old, some of them. And when people buy in this area, they are looking more at the location than they are the house itself. In fact, it may be that lots of times they buy a house simply to tear it down and rebuild there. So another thing that's going to be very important, we think, is the size of the lot. In other words, if you got a lot that's got a really high grade and it's on the water and it's a big lot, you're going to pay a premium for that. So I want to create another variable over here called square foot of the lot, and that's going right there, and I'm going to copy it down. And let's do another regression. So I go to my data tab, I come over on my toolbar to the area called analysis, and I'm going to select data analysis. Again, I'm going to select regression, and everything's already set up the way I wanted, except I need to add one more column. So I'm going to change that little R right there to S, and now we're ready to run, and we got our new regression model. Now our adjusted R squared, it didn't increase as much that time. It's up at about 0.63. Let's see, the previous time it was at 0.58. So we're looking at adjusted R squared of 0.63. The standard error got a little bit better, 123. And again, let's look at our prediction formula. We want to change those numbers into dollars. And I shouldn't have left off the cents, because the coefficients that go on to the square foot of the lot are actually in cents. You pay so many cents per square foot on the lot, 34 cents to be exact. So that variable made a lot of difference. It improved our forecast. But since square feet, these other numbers are like zeros and ones or fours or fives or sixes. Grades, you know, range from 1 to 10. The square foot of the lot could go from, who knows, it could be a 2-acre lot, and I don't know how many square feet 2 acres are, but it's a lot. We can go back and look in a minute and see what the range. But anyway, about 34 cents per square foot is how much you add to the value of the house. So you notice everything that we know about our prediction now is based on the lot itself. So finally, we say it might make sense to at least include the size of the house in our forecast. So let's go back and do that. Something that I hope you're noticing as we go through here, I'm not letting the computer tell me what to put in as my next variable. that's the ideal situation. In other words, when I build a regression model, I'll show you in a minute what happens when you just dump all the numbers into the regression and let it try to figure it out. But what I would like to do is to have subject matter expertise that tells me what should be important, and the regression model is simply confirming my subject matter expertise, and it's also quantifying it for me. So let's go back, and we're going to add the square foot of the house. And so I'm going to create one more variable here, and square foot living is the variable, and I want to copy it all the way down, and then I want to go to my data tab, over to my analysis toolbar, select data analysis, select regression, and I want to expand the input range of the X variable from column S over to column T, and OK, and here's my new regression. The R squared is now up to about 0.67. Previously it was about 0.63. So we only got about 4% improvement in R squared. And at that point I start saying, you know, I think I've milked about all I'm going to get out of the data, because if I'm only getting 2 or 3 or 4% by adding the rest of these variables, I don't really want to clutter up my model by having so many variables in there, and we'll talk about that in just a moment. And so the R squared is about 0.67. The standard error is now about $118,000, so plus or minus 3 of those, and that's, you know, not real close, but when you're talking about houses that range in price, but you know, up to $1.4 million, that's getting kind of in the neighborhood, I guess. And then I want to look at my formula once more to try to get some insights from it. And I need to format those cells again. And those are dollars. And it says if you want to predict the price of the house, start with the intercept again, which is negative, which doesn't have any physical or financial interpretation. It just says if you had a house with 0 waterfront, 0 square foot of lot, 0 square foot of living space, and 0 grade, that's what the formula would predict for it. The value for each unit of increase in the grade is about $81,000. The increment for waterfront, the difference between houses that are on the waterfront and houses that are not on the waterfront, has now jumped up to $200,000. The square foot is now at 29 cents, and the square foot of per unit of living space is $69 per square foot. So these variables change around, and the reason is, let's pretend I'd only put in a single variable, and that single variable was square foot of living space. It would have had a big number beside it because it is also correlated with those other variables, and it's trying to help incorporate those into the model. In other words, if the only variable I had was square foot of living space, it would say, well, the big houses tend to be on the best lots, and they tend to be the houses on the waterfront, and they tend to be the houses on the biggest lot. So if the only variable I had was square foot of living space, it would probably have a bigger coefficient than that in it. So now we have a model that's got about 4 variables in it, and I'm going to show you what would have happened if we hadn't have used our subject matter expertise to develop our model. So what I'm going to go do is I'm going to back and I'm going to develop a regression model, and it just says I'm going to dump all the numbers in the computer and let the computer sort it out. So again, I select data, I go over to the analysis toolbar, select data analysis. I'm going to do a regression. My input is still the price. The Y range is still the price. For the X variables, I'm going to predict everything. I'm going to put in everything that I have there. The number of bedrooms, the number of bathrooms, the square feet, the size of the lot, the waterfront, the view, the condition, the grade, the square foot above ground, the square foot of the basement, the age of the house, the square foot of living space based on a standard that was established in 1915, which is different from the one we use now, the square foot of the lot based on the 1915 standard. I'm going to put in everything except the zip code. The zip code's the same for all of the houses, so there's no use in putting that in. And now I'm going to do my regression model. And you notice the R squared for this model is only a little bit larger than the one that I got using only 4 variables. And if I look at all of these, and the standard error is a little bit smaller than what I had before, and you'd say, well, why not use that anyway? Well, there's a difference between fitting this data set and being able to predict the price of a house that is not in this data set. So if I have one regression equation that uses only 1 or 2 or 3 or 4 variables on this data set, I can fairly safely assume that it'll give about the same results on the houses that come up in the future. On the other hand, if I've got this model that has all of these variables, it's going to fit this data set quite a bit better than it will another data set of houses that come up in the future. So that's one reason why I want to end up with the model that has the fewest number of parameters that gets the job done. So if I've got lots and lots of different possibilities, and I do, I could take lots of different combinations of variables here, and if I have a lot that all give an adjusted R squared. By the way, I looked at the wrong R squared there. That's the adjusted R squared, which is almost the same as what we had before. On sheet 5 it was 0.66, and on this one it's still about 0.6. That's the reason why you use the adjusted R squared, by the way. It says it'll take into account the fact that I've only got so much data, and the more variables I have to estimate from, or the more parameters I have to estimate from that data, the less confident I am in the quality of the estimate. So it adjusts the R squared to account for that. So the adjusted R squared is about the same. So if I've got lots of different models to choose from, and they all have about the same R squared, or same adjusted R squared, I want to pick the one that's got the fewest number of parameters. One is I have more confidence that it will work in the future. But the other, you can see by just looking down through here and trying to make an interpretation of these numbers. It says, how much is an additional bedroom worth? And it says minus $37,000. That doesn't make any sense. Well, you know, you could probably make up some kind of a story to explain that, but it probably says the number of bedrooms is highly correlated with the number of bathrooms. It's highly correlated with the square foot of the living space and the square feet above ground and all these other variables. So somehow it showed up in those other variables, and it ends up with a negative coefficient here. If I say, what's a square foot of a house worth? I could say, well, you know, square foot shows up in a lot of different forms. I measure it in two different ways here. One of them's got a 81 in front of it, and the other's got a 44 in front of it. By the way, those are dollars. I forgot to reformat them. Let me do that. And so if I'm trying to make sense and say, certainly if I have a model, I would like it to tell me, how much difference does it make if a house is on the waterfront? How much difference does it make as the quality of the grade increases? How much difference does it make as the size of the lot increases? How much difference does it make as the size of the house increases? When I've got all these similar variables in there, it's really hard to say, because the square root of living space has got this coefficient. The number of bathrooms has this coefficient. Those two variables are certainly correlated. Then I've got this other way of measuring living space down there that's got a 44 in front of it. And then I've still got this other measure of living space that's square foot above ground, and it says that variable actually ended up with a value, a coefficient of 0. So it makes the equation much harder to interpret if I make it too complicated. So this is sort of turned out to be both a demonstration of how you compute regression models, but also a little bit of explanation of how you would go about finding the regression model that you want to use in any particular application. So that's all that we have for this, and I'll post the data set so that you can practice doing some of these models yourself.